Okay, they end up doing a supercomputer simulation of it. And that's the closest thing that they were able to come up with. It's not the rotation of the core. It doesn't have much to do with it. And you got these molten metals just flowing all over the place. And then they give you
Today,
the magnetic field pointing in that direction. Okay, are we getting stuck?
the Earth's magnetic field runs from south to north, which is why compass needles point toward the North Pole. And recent lava flows record a field pointing north. But 50 years ago, when scientists measured the magnetism trapped in older lava samples, they made a startling discovery. The microscopic magnets within the lava were all pointing south.
When we go back about 700,000 years, we find an incredible phenomenon. Suddenly, the rocks are magnetized backwards. Instead of them being magnetized to the north, like today's field, they're magnetized to the south.
It seemed that prior to 780,000 years ago, Hawaiian lava must have cooled within a global magnetic field that was running to the south and away from the north, exactly the reverse of today. The bizarre implication was that at some point, the entire global magnetic field had done a sudden 180-degree flip, completely reversing direction.
Okay, guys, we're in the midst of a reversal process, and that's the reason why the Earth's magnetic field is becoming weaker. It's not a big deal, so we're going to be exposed to some more particles coming from space. The cancer rates are expected to go up probably about 10%. And then the magnetic field is going to return, and then things will be okay. All right, that's as far as it goes. All right, so exactly how this happens, how the Earth's magnetic field is generated, it's still under study. It's a bit of a mystery.
In the 20th century, daily life has been revolutionized with the help of small, compact electric motors of less than 1 horsepower. 90% of all motors built today, they quietly and efficiently power our tools, our car windows, and most of our world.
So electric motors, how do they work? All right, something that we'll discuss later. But let's talk about something a little bit more interesting. Let's talk about blue light. Oh my God, this is exciting. All right, so what looks like blue light? Evidently, when you place a magnet right next to it, it becomes deflected. So which means that whatever it is that you're looking at, this beam is composed of particles, charges. And by looking at the direction of deflection, it was discovered that this beam is composed of negative charges. That's what I'm just describing as the discovery of the electron in 1897. The guy who discovered it, J.J. Thomson, for which he won the Nobel Prize in 1906. All right, so by chance discovery, you could win the Nobel Prize about 100 years ago, evidently. So that's kind of cute. This little setup that you guys are looking at later becomes the TV tube. This is the cathode ray tube. All right, so why does the electron beam deflect? Let's check to see if this thing's going to work. All right, so as you well know, when the charges go across the magnetic field, they will experience a deflection.
Here's
Well, I didn't realize this thing was that small.
the one that's on the top.
Or this guy's fingers are really big.
Here's one that's on the bottom. And a stream of electrons comes through that point there. Inside this case, there's a high voltage grid and a little device that gives off electrons. The electrons see the high voltage, they get accelerated, and some of them pass through a small hole in the center. The ones that pass through come and they will hit a screen. And when those electron beams hit the screen, causes it to glow. If I were to apply a positive voltage to the top plate, as the negative electrons went through, they would be deflected. They would go upwards as a result of that positive voltage. On the other hand, if I were to put a negative voltage on the top plate, the electron beam would go downwards as a result of that. I can alternate the beam electrically, alternately going up and down by altering the positive and negative aspect of that beam. This is the fundamental principle in the operation of television. I get a device that causes it to deflect up and down, vertical. I can also do the same thing horizontally with 2 more plates that control the horizontal axis. And by combining the 2, I get 45 degrees. Now, as the charged particle travels through the air, kind of it acts like an electron going through a wire in as much as it creates a magnetic field around it. If I were to bring a magnet nearby, I could deflect the beam with a magnet. This is cool. Electricity and magnetism inexplicably connected. This is the basic principle for television. Excited electrons hit the screen, causing it to glow. They also create a magnetic field, which I can change with another magnet. Each one of these lines that you see is called a flux line, or line of magnetic flux. The closer together they are, the stronger the magnet. That phenomenon is known as flux density, the ratio of flux lines per given area. Don't do this to your television at home. It leaves a permanent magnetic charge, which will ruin your TV set. This does not happen with plasma TVs or LCD TVs. They work on a completely different principle.
By a magnetic field today. So we have the electron tube set up with the power supply,
Okay, let's move forward.
accelerating voltage, up the amperage, the electron tube, 2 kilovolts, and this will produce a nice bright beam in the electron tube. You can see that beginning to show up there pretty well. And now I'm going to turn up the amperage in the coils, produce a uniform magnetic field across the tube with a pair of Helmholtz coils that was made here at the university. So I'm going to start now turning up the voltage on the Helmholtz coils, and we'll see what the interaction is between the magnetic field and the electrons. Right now I have about 1/4 amp of current going through the coils, now about 1/2 amp, and 3/4 amp, and now about 1 amp of current. You can see a nice deflection of the electron beam in the tube there.
All right, so let's go with this simple explanation and then come up with a mathematical version of the same thing. So static charges, nothing happens. Charges moving parallel to the magnetic field, nothing happens. When a charge goes across the magnetic field, obviously it's going to experience a deflection. All right, so let's express that mathematically. All right, and then let's just focus on the basics. All right, so this is where we are at. This is the right-hand rule. Obviously, here's a vector, velocity vector. And the magnetic field is in this direction, velocity vector is in this direction. All right, just line up your thumb in this direction, the fingers are in this direction, so your palm points in the opposite direction. So we talked about that. Okay, so one of the things that I want you to notice is the velocity vector does not need to be 90 degrees to the magnetic field vector. Okay, there could be a bit of an angle there. All right, so this is known as the cross product. All right, so this is from Calc 3. So what that means is this vector is going to be a cross product of this one. And so when you have these two vectors like that, the cross product of these vectors will be perpendicular to the space or the area that this one is going to spawn or spin in this direction. All right, so and what that means is, I think we may have talked about this before. I'm kind of afraid to get out of this page because as soon as I do that, I'm afraid this thing is going to die. All right, just want to briefly touch on the mathematics regarding this. All right, guys, here's the meaning of a cross product. You may have a vector here, and you may have a second vector in this direction. This is vector A, this is vector B. Cross product of A and B is going to be a vector, which is C, which is going to be perpendicular to both of them. That's what it means, mathematically. All right, this is just a mathematical expression. And those of you guys who haven't taken Calc 3, it's not a big deal. Physics is one of the best ways you can learn math. All right, so I'm just going over the idea. So A cross B is going to be C. So A cross B, notice that A and B, there's going to be an angle in between. So I'm just going to place the angle here. All right, so let's use the same angle, which is going to be theta. So this expression that you're looking at could be expressed as a scalar, in a scalar form, I'm going to say. And in order to express it in a scalar form, we can just say, all right, so it's going to be A cross B. So it's going to be A times B times the angle of, the sine of the angle in between is going to give you C. And all of a sudden, we were able to express the entire thing here as a cross product. All right, so this is from Calc 3. This is what it means. All right, so this is a review. So this right-hand rule that we've been discussing originally comes from this cross product. All right, this cross product is usually represented as a right-hand rule. Let me go to PowerPoint. Let's check to see how this looks like. All right, so the right-hand rule comes out of here. All right, so what you need to do is you need to, original form from calculus of the right-hand rule is you will line up your fingers in this direction. And then what you need to do is you need to curl your fingers in the direction of the second vector, which is B in this case, and your thumb is going to point in the direction of the force. All right, so this is the intended interpretation of the right-hand rule. The interpretation that I gave you is the one that we use in physics because it's more practical. All right, so this is the cross product. V cross B is going to give you F. All right, that's what it means. V cross B is going to give you F. Or if this is A, this is B. A cross B is going to give you a C. It's the same idea. All right, so that's the meaning of the cross product. So for the positive charges, you use the right hand. For the negative charges, you use your left hand. All right, so that's the idea. All right, so V cross B. All right, so this is V. All right, cross B. All right, is going to give you C. A cross B is going to give you C. V cross B is going to be F in this case. And this is the scalar way of expressing it. Okay, guys, understand that this force is going to be maximum when this angle is 90 degrees. That's it. All right, so the strength of the force depends on the angle between the velocity vector and the magnetic field. Okay, so speaking on which, let's just play with the concept a little bit. So what do you suppose the force is going to be when the angle is 0? All right, so what happens to the force if the angle is 0?
0.
All right, it's going to be 0. Okay. All right, let's just make this seamless so I can play around. All right, so when the angle is 0, sine of 0 is going to be 0. So which means that the force is going to be 0. All right, so when the charge is moving parallel to the magnetic field, it's not going to experience a force. That's what it means. We kind of knew that. Okay, another way of looking at what if it's not moving? If it's not moving, what happens? This is going to be 0, right? So which means that the force is going to be 0. All right, so when this is 90 degrees, obviously this is going to be 1, so it's going to experience the largest force. All right, when this is 0, the force is going to be 0, so it's not going to experience any sort of force on it. All right, having said that, let's move on to our problem. All right, so this is the interpretation that we're using, but the original interpretation comes from calculus. So the charges going across the magnetic field, they will experience a deflection. In fact, if you place a charge inside a constant magnetic field, it's going to go into circular motion. Case in point, and this is the one that we will focus on. We'll do a problem.
Welcome to the demo prep room. We're sitting here in the dark because we're going to show you that a charged particle beam does indeed go in a circle when you put it in a uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun in it. An electron gun really just means a heated metal filament that's easy to draw electrons off of.
All right, so electron gun is, in this case, is your capacitor.
Near the gun that you can now see glowing orange is a little metal plate that we put in a large positive potential. So that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas. Now you're seeing the beam so that some of the electrons keep going and form a...
Okay, so let's get rid of this. All right, guys, you got your capacitor here, right? So this is your negative charge plate. This is going to be a positive charge plate. There's going to be a hole in the middle. Notice that they were able to generate an electron beam right there. All right, so they will use a magnetic field within this region. So they will just, this entire region is going to become magnetized. So they are going to actually create a circulating electron beam
that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. So you're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam if you bring in a strong concentrated magnetic field. But what we're here to do is to create a uniform field, and that's what these two big coils are. So this is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here, we're going to start turning it up, and you can see it's starting to curve more and more. And right now, it looks like it wants to make a circle, but the radius is too big. It doesn't fit in the bulb. So if I keep turning it up, more and more current, bigger and bigger B field, eventually, there it is. It makes a circle. Perfect circular motion, going right back to where it started. And if I turn the magnetic field back down to 0, straight again. So there's direct visualization of the circular motion of charge in the magnetic field.
All right, this is really, really well done. Problem number 2 is the one that I want to do. Problem number 1 is for kids. Okay, so problem number 2 is interesting. Okay, so let's focus on problem number 2. Problem number 1 is just the application of the formula, so I don't care about that. All right, so once again, we got the proton beam. All right, so the protons will be accelerated within a capacitor. The potential difference between the capacitor plates is going to be 2100 volts. All right, so there's going to be a small hole in the negatively charged plate, so the protons will just shoot out of it into a region which has a constant magnetic field, which is going to be perpendicular to the motion of the charges. So find the speed of the proton as it leaves the capacitor, find the change in the proton's kinetic energies, and find the radius of the circular path on which the proton moves in a magnetic field. All right, this is somewhat challenging. Normally, I would make it a lot more challenging than that. Okay, guys, just for the hell of it, I'll make it challenging. All right, I'm going to skip A, B, and I'm going to just move on to C. I'm going to make it more like real life. Imagine that there's no A, there's no B. Just find the radius of the circular path given all the information which is given. All right, so let's do that instead.